So good morning, welcome back, and this is the continuation of the last lecture. So in the last lecture, we have seen the theory behind the deflection system, uh, how we get the equation of a parabola, and thereafter what happens. So these were the things we have seen last class, and one important conclusion was that the deflection D cost is directly proportional to the deflection voltage ED. So all other factors remain constant. So this was the equation, last equation we have seen that D is directly proportional to ED. So there exists a linear relationship. So I made two very important statements. As it is directly proportional, this is a linear relationship. So that means that if ED is constant, then deflection occurred is also a constant. But if ED is time varying, if we apply a time varying quantity across the deflection plates, then similarly the deflection also will be time varying. That is very important. I repeat, if we apply a time varying signal across the deflection plates, then we get a time varying deflection. So according to the voltage applied to ED, the nature of voltage applied across the plates, we get the same nature deflection on the screen. So that is very important. Okay. Now, incidentally, when we have discussed the deflection system, we have seen the vertical deflection plates. That is, there you can see that the plates are placed horizontally. They are placed horizontally. Upper as well as lower plate are placed horizontally, and in between you are having vertical electric field lines. So what is the nature of vertical deflection plates? The plates are placed horizontally and the electric field intensity is vertical. So that will cause a vertical deflection. Okay. Now, two important things we have to note. So one more thing, I'll make a statement now. That is, so what is a signal we apply across the vertical deflection plates? I told if we apply a time varying quantity, a time varying deflection will be occurring on the screen. So what is the nature of what type of signal we apply across the vertical deflection plate? We apply the signal under investigation across the vertical deflection plates. I repeat, we always apply the signal under investigation across the vertical deflection plates. Now coming back, there is one thing we have to see, that is deflection sensitivity. What is deflection sensitivity? It is given by D by ED. D we know, ED also we know. So if we substitute the value for D, this is what we get. We have got a final equation for D, substitute that, this is what we get. Okay, so we can see that in order to improve the sensitivity, we have to reduce the acceleration voltage. That is, we apply some acceleration voltage of plus 1500 volt across the pre-accelerating as well as accelerating anode. So that should be reduced. So if that voltage is reduced, then naturally the acceleration or the velocity of the electron beam hitting the screen will be reduced. So if that acceleration or velocity is reduced, what happens? The luminosity or the brightness of the spot reduces. Okay. Now, so if suppose that is one thing, if you want to increase the sensitivity, the luminous spot or the brightness of the spot reduces. So that we don't need to some extent. So you need sensitivity, but you need not need the brightness to go down beyond a limit. So if we keep the accelerating voltage a high value, then what happens? If we keep the accelerating voltage a high value, then to cause corresponding deflection, that is, if this value is also high, to get for a given deflection, the ED also should be a very high value, because this is a very high value. For getting a given deflection, this voltage also should be a very high value. That is, the voltage across the deflection plate system also should be a very high value. Okay, so one disadvantage is that if you see, you need to improve the sensitivity. For improving the sensitivity, you have to reduce EA. In that case, the brightness of the spot reduces. So to increase the brightness of the spot, you have to increase the value for EA. So if you increase the value of EA for a given deflection, you have to have a very high value for ED. So if EA is increases, it requires high deflection potential ED for a given. So what happens? So acceleration of the beam increases, and that will be such highly accelerated beam will be very difficult to deflect, and such a beam is often called as a hard beam. A highly accelerated beam will be very difficult to deflect, and such a beam is called a hard beam. So usually these are the values of sensitivity used in CROs, that is 0.5 mm per volt to 1 mm per volt. So this is the thing we have to remember in the differential system. Okay, next we are moving to the screen. So what is a screen? See, this is the screen that we are seeing often. So this is called a graticule, and on the front you're having a face plate, which is a glass, which can be a glass or it can be fiber. Fiber is also possible, and glass is also possible. So the face plate is either made of glass or fiber. Okay, and these lines are provided on the face plate for easiness of taking measurements. Okay, so okay, we are very familiar with. So this screen is called the CRT graticule. So behind, so this is the front plate we are seeing. Behind the front plate there is another side of the front plate. We are seeing the front side of the face plate. On the backward side of the face plate we have the phosphor coating. The full back side of the faceplate is coated with phosphor. So what is that phosphor? So what is the quality of that phosphor? I already told that in the first lecture itself. Phosphor that we are coating should have very high persistence. Otherwise, we cannot make any meaningful conclusions from that variations in luminous spot or stylus. Okay, so what happens? That is, when an electron with a constable velocity, if it is having constable velocity, it is having some kinetic energy. When an electron hits with some kinetic energy, the crystals, the phosphor crystals, will raise its energy level. When it raises its energy level, light will be emitted or luminosity will be formed, and that phenomenon is called cathodoluminescence. So when the electron beam strikes the phosphor crystals, it raises their energy level, and this is called cathodoluminescence. And that is one thing. That so when it hits, this phenomenon takes place, and we can see a bright spot on the screen. Now what happens when there is no electron beam? When suddenly the electron beam is stopped, what happens? The phosphor excitation, when the electron beam is switched off, the phosphor crystals return to the initial state. Okay, there is a stable state, the ground state, the stable state. When the electron beam is switched off, it come back to the initial state. And when it come back to the initial state, there is a release of quantum of energy in the form of light, and this is called phosphorescence or persistence. So this is what is very much required. That is, when the electron beam is switched off, the glow suddenly will not go off, and due to the phenomenon of phosphorescence, that glow will persist for some more time, and that is required because at least the persistence should be equal to the persistence of I to make some meaningful conclusions. Okay, now another thing we have to make out is that, so these are the different classes of phosphor used. You can just simply refer the literature that is based on how burn resistance is implemented. That is, I told that if I consistently make the luminous spot at one point of the screen, there are chances for that spot to become burned. So phosphor should have some sort of a burn resistance, and that is how they are classified here: low burn resistance, medium burn resistance, and high burn resistance. Okay, now so we have seen the screen. Behind, on the other side of screen, we have the phosphor coating, and after that, immediately after that, there is no contact with the phosphor, but there are on the non-viewable side. So behind the phosphor screen, we don't know what is happening. We can't see anything behind that because there is a phosphor coating. We cannot see what is inside the CRO. So just behind that, there is no contact, but just behind the phosphor screen, we have a aluminum screen of the same size of the screen. Aluminum screen, and this aluminum screen has a size, and this is the size of that aluminum screen. A thin film of metal such as aluminum, 0.1 to 0.15 micrometer, is usually deposited on the non-viewing side. That is phosphor. We have the faceplate. On the other side of the faceplate, we have the phosphor coating. After that, there is no contact with the phosphor. After that, we are having a very thin, fine film of aluminum, and that why it is of micrometer thickness. And what are the effects of that thing? That is, it has three uses. One is that when an electron hits the screen, of course, energy is liberated, so heat also will be liberated. So this adjacent aluminum thin film. Aluminum, we all know it's a good conductor of heat, so that will act as a heat sink. So that will reduce the danger of phosphor burn. That is one thing. And the other thing is that when an electron beam hits the screen, that is, the light may scatter. The light emitted or excitation energy or the luminous energy will be produced, and that will get scattered. So the aluminum will collect such scattered, and they will return or reflect the light back to the screen. So that will act as a reflector. That is one. So that increases the brightness of the screen. That is the second thing. And the third thing is that when the electron strikes, secondary electrons are generated. When the electron hits the phosphor, secondary electrons are generated, and these secondary electrons have something that is they sometimes get attached to the screen, the phosphor screen. The secondary electrons get sometimes attached to the phosphor, so they get digged in the phosphor. So if such secondary electrons are present in the phosphor, electron is finally coming to the screen. So if electrons are already present, if some secondary electrons are already deposited as residue in the screen, what happens? The coming electrons will feel a force of repulsion. So what happens? The acceleration of the beam reduces, and the electrons hitting the screen, acceleration will be reduced, velocity will reduce, and if the velocity reduces, what happens? The brightness reduces, and that is called a negative voltage buildup, and that will of course produce a very disadvantaged situation in the screen. So you don't want secondary generated electrons to stay back as a residue in the screen. If that happens, the coming electrons will face what? Force of repulsion, and that will indeed reduce the acceleration, and that will lower the brightness. So that is called negative. So what is the solution? This aluminum screen is connected to another thing called an aquadac. What is an aquadac? I will show that. That is aquadac. So what is aquadac? Aquadac is here. This is my aquadac. There is a coating here. This is called aquadac. There is also an aquadac. So what is aquadac? All along the CRT tube, we have a shallow mask tube, and a common in television. Sorry, I am reading the wrong thing. That is, bombarding electrons striking on the screen release secondary emission electrons. These secondary electrons are collected by an aqueous solution of graphite called aquadac. So I have shown where this aqueous solution of graphite is placed. This is a place where we place the aqueous solution of graphite. So that is called aquadac. So these secondary electrons are finally collected by the aquadac. So how can this aquadac collect the secondary electrons? This aquadac is connected to the second anode. That is the accelerating anode. We connect the aquadac. So accelerating anode, we know it is a high positive potential. So that high positive potential will absorb or will attract the negative electrons, that is the secondary electrons. So we have the screen, the aluminum screen. So aluminum screen is placed besides the phosphorus screen. The phosphorus screen, if it has the secondary electrons, so this aluminum screen is connected to the aquadac, electrically connected to the aquadac. Aquadac is electrically connected to the positive high potential. So when we have the secondary electrons on the phosphor screen, these secondary electrons will be absorbed by the positively connected aluminum screen, and this aluminum screen will transfer the secondary electrons to the aquadac. Aquadac will transfer the electrons to the anode, which is plus 1500 volt. So this electrons will be attracted by or collected by the aluminum sheet, and aluminum sheet will give that to aquadac. Aquadac will transfer the electrons to the positive potential or the high voltage. Thus it will actually negate the formation of negative voltage on the screen or accumulation of electrons on the screen. Okay, now we'll see the deflection system in detail in the next class. I hope this is very simple, and I had a figure with me, but today I don't have the time to explain. This was a type of thing I have to explain, very interesting thing. So we'll see that in the next class.